Hey everyone, welcome back to another video by Camroom 5. In today's video we are continuing the idea of mass spec. We'll be talking about the M+1 peak and we'll also be talking about the M+2 peaks. In order to understand them better, let's focus on this mass spec. The highest peak, the one with the biggest molecular mass, represents the molecular ion peak, the one which hasn't been fragmented. But I can see there are two peaks. Is it the 151 or the 150? Actually, both of them are the molecular ion peaks. But why do we have two peaks for the same molecule? The reason for that lies in how the mass of carbon changes. When we talk about carbon atoms have two main, and by main I mean stable isotopes. The first isotope has 6 protons and the second one also has 6 protons. But the number of neutrons are 6 or 7. That means the proton number is 6 both times. The number of neutron could be 6 or 7. Which means the first carbon atom has a mass of 12 units, the other has mass of 13 units. Their abundance in nature is almost 99% and 1%. When we take a relative value, it almost becomes that if the relative abundance of carbon 12 is 100, carbon 13 would have been 1.1. And this is an almost value which gives us a good estimate. Now, how do we use that? You should know one thing, that the abundance of the peak depends on number of carbons. The peak, the height of the peak, the abundance of the peak is proportional to the number of carbon atoms in the molecule. If you have more carbon atoms, for example, if you have n number of carbon atoms, where capital M represents the abundance of the carbon 12 peak and M+1 represents the abundance of the carbon 13 peak, then using the relative ratio of 100 is to 1.1, we can find the value of number of carbon atoms. Capital M, I repeat, is the abundance of the M peak which is made by carbon 12, and M+1 means the abundance of the peak which is made by carbon 13. And now using the ratio, we can solve this question. You can see the question is about a compound D where you have carbon, hydrogen and oxygen. In this question, the M peak has an abundance of 33.9 and M+1 peak is 3.4 times abundant. M peak was made by carbon 12 and M+ was made by carbon 13. Now using the ratio of 100 and 1.1, we can solve for n, which means the number of carbon atoms in a compound. Doing the basic arithmetic, we can find n, which in my case turns out to be 9.1ish. So let me write that. It's going to be 9.1ish, and that is not a whole number, so we make it 9 carbon atoms. Now the question is also about the molecular formula. You can see the molecular mass of the compound is 150, or you can say 151 gram per coulomb. So ask yourself, 9 carbons are already there. What's the mass because of them? So 9 carbons times 12 gives you 108 units of mass. If you were to consider, for example, if one oxygen was there, it would give you 16 units of mass. So let's suppose if oxygen was 1, it would give 16 units of mass. And then, for example, even then it would not be enough, because you have to reach a mass value of 151 or 150, which is way higher than the mass provided by carbon and oxygen right now. You can't put so many hydrogens over there. For example, it becomes a mass of 124. You can't put almost 26 hydrogens, because in order to make it 150, you can't put 26 hydrogens. So you need to think about putting more oxygens, because you can't put more carbons. Obviously, you know carbon is 9. So you need to think about putting more oxygens. Carbon is 9, we know, so that's a mass of 108. Think about putting 2 oxygens. That would give you a mass of almost 32. And then you can get a total mass by adding 32 and 108 as 140. So in order to make 150, you need 10 more hydrogens, and that is okay because 10 hydrogens can be around 9 carbon atoms. So your compound becomes C9H10O2. 9 was fixed, 2 you figured out, and 10 was remaining. It could be having carbon-carbon double bonds, that's why hydrogens are lesser, but at least it fits the data of the question. Now the last part is concerned about the mass spectrum has a peak 119. So if 150 was the molecular ion and you can see 119 is there, what has been lost? So 31 unit has been lost. In order to compensate for 31 units, C2H5 comes in your mind. But that is 29 units of mass, so that does not fit here. Make a CO and let's put 3 H's around it, so that will give you a mass of 31 units. That is a better explanation here because COH3 gives you a mass of 31. Maybe this is the part that has been lost. For example, this is a structure of a primary alcohol from the corner. Maybe this has been lost. Now let's talk a little about the M+2 peaks, which are made by halogen atoms. For chlorine, we have 2 isotopes, both with 17 protons, but the number of neutrons are different. The first chlorine has a mass of 35 and the second one has a mass of 37. Their abundance in nature is not equal. It's almost 3:1, which means 75% is chlorine 35 and 25% is chlorine 37. Similarly, for bromine, we have got 2 isotopes. The one with bromine 79 units of mass and the other bromine has 81 units of mass. Their abundance, as contrary to chlorine, is 1:1. So 50% abundance of each bromine isotope is there. Now imagine a methyl chloride, or you can say chloromethane compound. The molecular mass of this compound could be 12 plus 3 times 1 because of the hydrogen. And if the chlorine one is a 35 isotope, the total mass turns out to be different. And if it was chlorine 37 isotope, the total mass would be different. It would be 50 and 52. You can see because of the chlorine's identity, the mass changes by 2 units. Their abundance is going to be because of M and M+2. The +2 means the chlorine with 2 more units of mass. Imagine now bromomethane. When you're trying to find out the molecular mass of bromomethane, you're going to have a similar kind of calculation. That one time you'll have the bromine with 79 units of mass and the other time you'll have 81, which gives you 94 and 96. These 2 masses are for the same bromomethane. One represents the molecular peak and the other represents the molecular +2 peak. In case of chlorine, the abundance is going to be 3:1, and in case of bromine, it's going to be 1:1. Now let's do this past paper question to make our understanding more solid. Natural bromine, which is Br2, consists of 2 isotopes, bromine 79 and bromine 81, in roughly equal proportions. The mass spectrum of bromine consists of 5 peaks. Suggest the mass numbers of the 5 peaks and the identities of the species responsible for them. We know the actual bromine is Br2, right? So there are 2 atoms mainly. Imagine your first bromine molecule when first of the atom has a mass of 79 and the other also has a mass of 79. In this way, the total mass is going to be 79 times 2, and this molecular ion is going to have a mass over charge ratio because of the 2 similar atoms, and that's going to be 158 units. Imagine another bromine molecule where first of the atom was 79 but the second was 81 units. In that scenario, our mass over charge ratio is going to be 2 units more because of the one bromine atom which has 2 more units of mass. The third bromine molecule could have both bromine atoms with 81 units of mass, and the total is going to be even 4 times more than the first possibility. Imagine the splitting happens and you receive 2 bromine atoms. So the first one is going to be having 79 units of mass. The other bromine atom, which is now an ion, sorry, I should rather say bromine ion, has a mass of 81 units. So these are the 5 possibilities. Suggest the ratios of the relative abundances. So we know that bromine 158, the bromine molecule with 160, and the bromine molecular ion, because of 162 I should say, are made by a combination. The first one had a combination of 79 plus 79. The other was made by the combination 79 plus 81, and the other was 81 plus 81. They all exist in an abundance of 1:1. So this way the question becomes very simple because the relative abundance is going to be 1:1:1, because all three have a relative abundance of 1:1. Even the one with the smallest masses 79 and 81 have a relative abundance of 1:1. Now let's look at this question where it says the mass spectrum shown was obtained from a compound of formula CpHqX, where X represents a halogen atom. It could be bromine or chlorine. Deduce the identity of X giving a reason. Now if you look at the molecular ion peak, there are 2 main peaks and each one is followed by a smaller one. There's a peak at 122 and there's another peak at 124. Why do we have M peak and M+2 peak? That's obviously because of a halogen atom. What kind of relative abundance is there? Is it 1:1 or 3:1? It's definitely 1:1, and that is why we know that it is bromine, because in bromine the mass 79 and 81 have a relative abundance of 1:1. The smaller peaks that you see followed by the bigger peaks are because of the carbon 13. So 122 and 123 are also carbon 13 peaks. Our answer is going to be bromine is the X, as the ratio of M and M+2 peak is 1:1. We follow our answer by saying that bromine 79 and bromine 81 exist in 1:1 ratio. If the relative heights of the M and M+1 peaks are 9 and 0.3 respectively, calculate the value of P. So carbon. We use the same formula to calculate the number of carbon atoms here. We do the basic arithmetic where M peak is 9 times and M+1 peak is 0.3 times. We solve the answer for N. 0.3 times 100 divided by 9 and 1.1. N is going to be 3.36 here. We can't put a decimal number here, so the value of carbon becomes 3. You can notice that bromine is already there and the molecular mass has to be 122-ish. So the molecular ion peak already has a mass of 122. We know that bromine atom is already there. So let's suppose we consider 122 peak and 79 units of bromine. So the mass contributors here are 3 carbons, which give you a mass of 36 units. And there's one bromine atom, which gives you a mass of 79 units. So how much mass is used up? 115 has been used up, and you wanted a total mass of 122. So 7 hydrogens were placed, and you get your final molecular formula. I hope this idea was clear to you guys, and in the next video we'll do some past paper questions. Stay tuned guys. Thanks.